The strange signal GPM J1839-10. Is it possible that it is from an extraterrestrial civilization? Two vital observatories on our globe assist us in observing any radio wave from space in the Earth's two hemispheres, the North and the South. The Very Large Array, VLA, is located in New Mexico, and the Murchison Widefield Array, MWA, is located in Australia. Both observatories contain massive radio antennas and radio telescopes spread across vast desert fields. Because they are vulnerable to radio waves from other stars and distant galaxies, these radio telescopes are strategically situated across the Earth to capture signals in both hemispheres of our planet with greater precision. However, scientists from the VLA and the MWA recently published an article revealing an unexpected radio signal source that reaches Earth every 22 minutes and whose nature is still unclear. This signal, known as GPM J1839-10, is unusual and remains one of astronomy's most recent mysteries. So what exactly is this signal that occurs every 22 minutes? Could it be an intelligent extraterrestrial race attempting to contact us? Join us to find out. Hello and welcome to Zeey. Subscribe to our channel and ring the bell so you don't miss our daily videos. It first appeared on Earth 35 years ago. To determine the source of the radiation, scientists chose to see whether something comparable had previously been observed in this area of the sky. And they were startled to discover the same signal at the same moment in the 2018 recordings. That's when they realized something interesting and unknown was causing the throbbing signal. Furthermore, when scientists examined the Very Large Array recordings, they discovered the GPM J1839-10 signal among recordings taken in 1988, when this radio telescope was just being started. This suggests that the human race has been capturing this signal for over 30 years, but due to the length of time, they have not paid attention to it until now. What kind of object may generate such signals? When scientists noticed that it was a pulsating signal with a precise and repeating frequency, they immediately thought of the only object in the universe capable of emitting that type of signal, a pulsar. A pulsar is a strongly magnetic, fast-revolving neutron star. Pulsar formation is inextricably related to the life and death of big stars. It all starts with the existence of a gigantic star, several times the size of our Sun, that has depleted its nuclear fuel. When these stars near the end of their lives, they experience catastrophic gravitational collapses, resulting in incredibly dense objects known as neutron stars. Matter is compacted to high densities during the demise of a big star. Electrons and protons combine to generate neutrons in this process, resulting in a neutron star with a very compact and highly magnetic core. After black holes, neutron stars are the heaviest objects in the universe. The mass of the Sun can be compressed into a radius of a few kilometers in this sort of star. As a result, the mass of a neutron star is so massive that if we could take a single tablespoon of material from one, it would weigh more than Mount Everest. Neutron stars formed under specific conditions where the angular momentum of their revolution is conserved can rotate incredibly quickly. This process can generate a massive magnetic field billions of times stronger than the Earth's magnetic field, and the combination of fast rotation and a powerful magnetic field will eventually lead the neutron star to spin exceedingly fast. Neutron stars can spin hundreds of times per second, with a spot on their surface traveling at speeds of up to 70,000 kilometers per second. Because of their dizzying speed, neutron stars that revolve so swiftly expand near their equator. Because of the centrifugal force exerted, these stars have a size of a few thousand meters, between 10 and 20 kilometers. Only the tremendous gravitational field of one of these stars can keep it from shattering into 1,000 pieces at this speed. On the other hand, neutron stars give rise to the pulsar which astronomers imagined when they saw the signal received at the VLA and the MWA. A pulsar is a fast-spinning neutron star that generates electromagnetic radiation beams. This radiation is observed by telescopes on Earth in the form of regular pulses. Although some pulsars radiate at other wavelengths, such as X-rays and gamma rays, the frequency of these pulses is typically in the range of radio waves. The precise mechanism that causes these pulses to be emitted is connected to the tilt of the neutron star's rotating axis and the corresponding magnetic field. If these two axes are not aligned, radiation beams can sweep through space like a lighthouse. When one of these beams is focused toward Earth, it is detected as an intermittent pulse of light that emerges and disappears with a known frequency and period. Pulsars have incredible rotational speeds. Some pulsars can rotate at high angular speeds multiple times per second. This fast rotation is caused by the conservation of angular momentum during stellar collapse. Pulsars are famous for their temporal stability in addition to their outstanding pulse emission capabilities. The regularity of the pulses is so perfect that it has been used to measure phenomena such as the expansion of the universe and the presence of large objects in its vicinity with exceptional precision. For many years, observing and researching pulsars has offered astronomers with a unique instrument for exploring numerous parts of the cosmos. The experimental testing of certain features of Einstein's theory of general relativity, the identification of planets orbiting pulsars, and the knowledge of the density of interstellar matter are among the most important contributions. Furthermore, pulsars have proved useful in studying magnetic field dynamics in severe astrophysical environments. These objects provide a unique glimpse into the severe circumstances encountered in neutron star cores. In summary, pulsars are neutron stars that revolve at tremendous speeds on themselves and release radiation beams visible from Earth as light pulses. Is it possible that the GPM J1839-10 signal is a pulsar? Initially, it was assumed that a pulsar was the best astronomical object to describe the GPM J1839-10 signal, but there was a major difficulty. The rapid spinning of pulsars is caused by the principle of angular momentum conservation after the gravitational collapse of a big star into a neutron star. A large star experiences gravitational collapse when its nuclear fuel runs out and it reaches the end of its life. This collapse compresses the star's matter to extraordinarily high densities, resulting in the formation of a neutron star. During this process, the initially rotating star contracts and its rotation speed rises as its size lowers due to the principle of conservation of angular momentum. Angular momentum is a physical quantity linked with object rotation that is conserved in closed systems when no external torque is applied. Simply said, if an item is rotating and there are no external forces acting on it, its rotation speed increases as its size decreases. By definition, the issue is that pulsars cannot rotate slowly. There is no minimum speed that a pulsar can spin at, however they typically spin hundreds of times per second. A pulsar cannot physically rotate as slowly as the GPM J1839-10 signal. In other words, because the GPM J1839-10 signal rotates too slowly, it is physically impossible for it to be a pulsar. But if that's the case, the original question resurfaces: what is the source of this enigmatic signal? Alright, before we continue, make sure you like or dislike the video so that we can make it better for you, and remember to subscribe and ring the bell so you will be notified when new videos are released. Magnetar. A magnetar is a type of neutron star with one of the highest magnetic fields ever seen in the universe. A strong magnetar is one of the most energetic and exotic types of matter in the universe. The development of a magnetar like that of a neutron star is tied to a supernova explosion. This catastrophic event occurs when a huge star runs out of nuclear fuel and collapses under its own gravity, killing itself. When a big star dies, its outer layers are expelled and the remaining core collapses to produce a neutron star. In the case of magnetars, it is thought that the massive star's original magnetic field is considerably enhanced during this process. The science underlying the phenomena seen in a magnetar is complicated and not entirely understood. However, there are various proposed hypotheses and procedures that explain some of these items' remarkable characteristics. Magnetic dynamics. The high magnetic field of a magnetar is critical to its behavior. The magnetar is thought to function like a huge magnet, interacting with the surrounding matter and causing powerful magnetic phenomena not seen in our solar system. Magnetic storms. Magnetars are said to be subjected to magnetic storms in which their magnetic fields undergo dramatic shifts. Remember that these events can cause powerful radiation emissions at multiple wavelengths including X-rays and gamma rays. This is crucial for understanding the GPM J1839-10 signal. Gamma ray emission. Magnetars emit gamma rays, the most energetic photons in the electromagnetic spectrum. This emission is caused by high magnetic activity on the planet's surface. Bursts and soft bursts. Magnetars have been linked to gamma ray bursts in some situations, which are highly energetic occurrences that release significant amounts of energy in a short period of time. Soft bursts of less intense but more frequent emissions have also been detected. Because of their understanding of magnetars, some scientists believe the GPM J1839-10 signal could just be a magnetar with a magnetic storm on its surface for 22 minutes. However, other scientists disagree. The fundamental explanation for this is that stellar earthquakes on the surface of stars are transient occurrences that cannot last more than 30 years. If the GPM J1839-10 signal was a magnetar, we would have seen it a few times and then it would have dissipated, but the fact that it has been there for more than 30 years suggests that it cannot be a magnetar. So what could this enigmatic signal be? White dwarf with a strong magnetic field. Another possibility is that this signal is from a white dwarf with a peculiar magnetic field. White dwarfs are the remains of a star the size of our Sun that died and left behind a compressed core. A white dwarf star can emit radio emissions comparable to those recorded with the signal, and because it is not a neutron star, it may rotate at a little slower rate, probably at 22 minutes, equivalent to the GPM signal J1839-10. The problem with this is that white dwarfs do not have a substantial magnetic field, unlike pulsars. Furthermore, current understanding of neutron stars holds that beyond a particular rotation speed known as the death line, their emissions cease. GPM J1839-10 is unique in that it not only rotates at an extraordinarily slow rate of around 22 minutes, but it also generates bursts of radio waves lasting up to 5 minutes, for which there is now no universally accepted scientific explanation. Even some experts do not rule out the possibility that it is an obvious signal planted there by an extraterrestrial culture far more evolved than ours. Now it's your turn, dear followers. We want to hear your ideas, so share them with us. What do you think the GPM J1839-10 22-minute signal is? Let us know what you think in the comments below, and remember to like and subscribe to the channel.